Hello, this is part of the Controlled Environment Plant Production Engineering / Technology Education modules that were developed and presented by The Ohio State University, Rutgers University, and the University of Arizona, with support from the USDA NIFA program. This module is titled Greenhouse Heating and is presented by A.J. Both at Rutgers University. The learning objectives for this module are, first, that by the end of this module you will be able to calculate the estimated maximum heat loss and the resulting heater or boiler capacity needed to maintain the desired temperature set points in greenhouses. And secondly, you're able to compare the cost impact of fuel sources used for heating greenhouses. Additional resources include a variety of websites, several books including Greenhouse Engineering, Energy Conservation for Commercial Greenhouses, Greenhouses, the book itself by Joe Hannon, Greenhouse Operation and Management by Paul Nelson, Ball Red Book, Volume 1, edited by Chris Bates, and the National Greenhouse Manufacturers Association, as well as ASABE, the American Association for Agriculture and Biological Engineers, have produced standards that may be helpful in terms of deciding what the heating capacity should be for greenhouse systems. Heat exchange processes in greenhouses rely on several physical processes, and they include conduction, which is heat transfer through materials or materials that are in contact with each other, through convection, due to the movement of fluids, including air and water, which includes evaporation and condensation of water vapor, which either requires heat, evaporation requires heat, or condensation releases heat. And convection can be either forced, that means with fans, or can be natural, where air or water moves because of temperature differences. And finally, heat can be transferred through a process called radiation. For example, the sun radiates to us and we receive that heat radiation from the sun, or surroundings that have a certain temperature radiate heat to you, or you radiate to your surroundings. And that radiation typically depends on the surface characteristics, surface emittance in particular, as well as the surface temperature. Greenhouse heat exchange can happen through various processes, and various components of the greenhouse are involved in heat transfer. This image shows you various processes where I've tried to, by color, indicate the various processes we just discussed: convection, conduction, and radiation. So for example, a heater will heat up the air in the greenhouse, and that air is then moved by convection through the greenhouse structure, perhaps with the help of a fan. So we have forced convection that blows that air throughout the greenhouse environment. Or we can have heating pipes that get really warm, that radiate some of their heat into the greenhouse environment, and it's then picked up by the various materials and items located inside the greenhouse. So this picture will give you an overview of what's happening in the greenhouse in terms of heat transfer. So how do we calculate what the heating or boiler capacity needs to be when we talk about greenhouses? First of all, we need to know how much heat is lost during the coldest time of the year. And we can do that by calculating various heat transfer processes. And those that are most critical are the structural heat loss that is happening by conduction and convection. So conduction through the material that the greenhouse is made of, and convection of air moving in and around the greenhouse. We have heat loss by infiltration, where we have air entering or exiting the greenhouse through unintended openings. And then we have heat loss around the perimeter where the greenhouse structure touches the floor, and especially when the floor is in connection with outside ground, and if that pathway is relatively moist, water is a very good conductor, then we can have significant heat loss around the perimeter. So if we know the amount of heat that's being lost through these three different processes, we can then calculate how much the heating system needs to make up in order to maintain the set point temperature. In some instances, in some locations, we need to make adjustments for when we are situated in locations with high wind conditions, or when we maintain a large temperature difference between the set point inside and the outside temperature. And I'll walk you through how we can make adjustments in a little bit. So the overall heat loss is then the sum of the structural heat loss, the infiltration heat loss, and the perimeter heat loss. And again, we need to make adjustments if needed, depending on high wind conditions and large differences between the set point inside and the outside conditions. So once we have the total heat loss calculated, we need to take into consideration that the heating system has some fuel conversion efficiencies. Most heating systems are not 100% efficient, so we need to take that efficiency in consideration in order to calculate the overall heating system capacity. So let's first look at the structural heat loss. It's a fairly simple equation to calculate what the structural heat loss is. It's the product of the heat transfer coefficient, that is a coefficient that is dependent upon the materials that the greenhouse is made of. It involves the surface area, so the surface area of the particular material involved in the heat transfer. We need to worry about the temperature difference between inside and outside. So the inside temperature is typically our set point temperature, and the outside temperature is what we call the design temperature. I'm going to talk about that in a minute. So the heat loss through the structure can then be calculated as the product of the U value of the material involved, the surface area involved, as well as this temperature difference between our inside set point temperature, which is typically the nighttime set point temperature, minus the outside design temperature. So we know pretty much what the inside set point temperature is. We can calculate the area by looking at the greenhouse design. We need to figure out the heat transfer coefficient by looking at a table once we know which materials were involved. And then the outside design temperature, as I mentioned, we need to look at a little bit more closely. So here you see a table, and this is most commonly how we approach this issue of the outside design temperature. We look at engineering tables for different locations and try to figure out what this 99% design temperature is that we need to use in our calculations. The other way we can do this is by looking at pictures of a map where the design temperatures are drawn in contour lines. So you see on the right-hand side in this image here a picture of the United States with a bunch of contour lines showing where or what the 99 design temperature is for different locations. So if you don't have a table, you can look at this image, but tables are typically a little bit better because you have a higher resolution in terms of the locations for where you want to design your heating system for. So we look at this 99 design temperature. That means that still 1% of the time the temperature may be colder. Remember, these are design temperature based on average measured values over a long period of time. But we cannot design a heating system that is able to provide enough heating capacity 100% of the time. And the reason is that we would have to design our heating systems to be very large, with a very high capacity, and that very largest capacity would only be used for a few hours every year when we do reach that very coldest temperature. So we make a compromise, we back off a little bit, we use a 99% design outdoor temperature, meaning that for some hours of an average year, this temperature will be lower, the outside temperature will be lower than this design temperature. And so we have to make provisions for dealing with that condition, but it at least allows us to design a system that is not incredibly large with a very high capacity to meet that absolute minimum temperature for the location you're trying to design your greenhouse for. So what do growers do when the temperature does drop below the 99% design temperature? They have two options. They can install additional heating capacity inside the greenhouse, or they can allow, and this is typically what happens, they can allow the inside temperature to drop a little bit because the heating system is not able to provide sufficient heating to maintain that set point temperature. So as long as the temperature inside doesn't drop too much, this is typically allowable, and we're only talking about a few hours every year, so often this is not an issue. But if it does become an issue, then the only option is to use additional heating capacity, for example in the form of kerosene heaters. So the next thing we need to figure out is the U value for the materials involved, and this table shows you several U values depending on the covering material, whether you have glass or plastic film, the polyethylene film, whether you use single layer or a double layer, whether you have an energy curtain installed, whether you use acrylic or polycarbonate. You can look up in this table what the U values are for these different materials and then use them in the equation to calculate the structural heat loss. The next thing we need to calculate is the air infiltration heat loss. Again, it's a fairly straightforward equation. You need to multiply a constant with the greenhouse volume, which again we can calculate from looking at the greenhouse design, the plans, or actually doing measurements. And we need to figure out what the number of air exchanges per hour is depending on how the facility was designed, whether the facility was new or a little bit older, whether it was made of glass, which typically has a lot of laps or a lot of potential gaps between the glass panes and the structure, versus a double poly film, which is typically fairly tight. So I show you a table on the bottom of this slide here with a set of values for this number of air exchanges, this unintended number of air exchanges depending on the air tightness of the structure. So you can look up what number is most appropriate for your particular calculation. You can plug it in the equation, multiply it by the volume and this constant, and multiply it by the temperature difference between the set point as well as the outside design temperature, and you can calculate the air infiltration heat loss. Some growers are really concerned about this air infiltration heat loss, and here you see an example of a grower who decided to install louvered openings, a roll-up system in fact, in front of the ventilation opening, in front of the fan that draws air out of the greenhouse, in order to try to prevent this infiltration heat loss or reduce this infiltration heat loss as much as possible. So in the upper right hand image you see a conventional fan system, fan installation with the louvers on the inside, and then air moves through the louvers to the fan blades and to the outside. On the bigger image you see this roll-up system that the grower installed to really make a good airtight seal when the fan is not operating, and therefore reducing infiltration heat loss in his greenhouse operation. Finally, we need to calculate the perimeter heat loss factor, and again you see the equation on this slide here. It's the perimeter heat loss factor multiplied by the perimeter in feet of the greenhouse, and then multiplied again by the temperature difference between our inside set point and our outside design temperature. So the perimeter we can calculate pretty easily by looking at the design of the greenhouse, and then the perimeter heat loss factor can be determined by looking at the table that I give you in this slide. Depending on whether the perimeter is insulated or not, you can find a factor that you need to plug into the equation to make the calculation. One of the issues that I get asked questions about fairly frequently is, in addition to insulating the perimeter of a greenhouse, do we need to insulate the entire floor of a greenhouse to reduce heat loss to the floor, to the ground below the greenhouse structure? And my answer is typically when the water table is relatively high in your location, that means you typically have moist soil directly underneath your greenhouse floor. And again, water is a very good conductor for heat. In that case, you may lose significant quantities of heat to the floor, to the ground underneath your greenhouse. And in that case, it makes sense to install a horizontal layer of insulation underneath your entire greenhouse. But if you're located on a site where the water table is relatively low, where the soil maintains dry conditions throughout the heating season, then it's often not needed to install a horizontal layer of insulation because dry soil is not a very good conductor for heat. In this slide you see examples of perimeter insulation being installed in both a greenhouse and a head house, the work area typically attached to a greenhouse. You can see here that insulation board is dug into the ground, preferably 2 feet deep, but some growers only go 1 feet deep. And if you make sure you make the connections tightly around the structural components, you create a pretty good barrier for heat loss around the perimeter that reduces the need for additional heating capacity. So it's an easy installation when you're building new. It's a little bit more complicated and more involved when you retrofit. But in either case, adding perimeter insulation can help reduce the heat loss around the perimeter of your greenhouse structure. Another example of a grower trying to improve heat retention inside the greenhouse structure is this image of a grower who installed bubble wrap along the north wall of the greenhouse. So this is a glass glazed greenhouse, and along the vertical north wall on the inside of the greenhouse, the grower installed bubble wrap. Other growers have installed opaque insulation board, which cuts down on the light entering the greenhouse structure. And that could be especially an issue in the wintertime when you already have low light conditions. So by using the bubble wrap, the grower increased the insulation of the north wall, but also allowed additional light to come through the structure to help improve the light conditions for the plants growing in the wintertime. I mentioned earlier that if you are located on a site with high wind conditions, or if you want to maintain a large difference between your set point and the outside conditions, we need to make some adjustments in our calculations. Basically, we're adding a multiplication factor or a fudge factor, if you will, to try to increase the overall heat loss from the structure to account for these special conditions. And so in this slide, I explain how you can calculate that multiplication factor depending on the temperature difference you're trying to maintain and depending on the average wind speed at your particular location. And so you can go through the example and understand how we create this multiplication factor to then use to increase the overall heating capacity for our heating system. So once you've done all that, you can calculate the overall heat loss for your structure. And again, you need to take into consideration the fuel conversion efficiency to be able to eventually come up with your boiler capacity. So I'd like to go through a simple example where we look at two different greenhouses. One is a freestanding greenhouse, 21 feet wide by 100 feet long, and one is a gutter-connected greenhouse where we have two of those greenhouse sections attached to each other. So each section is 21 feet wide by 100 feet long. Both have 14-foot sidewalls and have an arched or a curved roof, and the roof peaks at 19 feet. So you can go through the calculations that I show here and calculate first what the total surface area is of both of these structures. And you can already see by looking at the ratio of the surface area to the floor area that ratio is smaller for the gutter-connected structure. And that means, of course, there's less surface area per unit floor area and in the gutter-connected structure, and therefore per unit floor area we have less heat loss, and we therefore need less heating capacity in the gutter-connected system. The next slide shows you then how to calculate the structural heat loss, the infiltration heat loss, and the perimeter heat loss to come up with the overall heat loss to the structure. And again, you see that the heat loss for the gutter connected house per unit area is smaller than the heat loss for the single freestanding greenhouse. So here you have an example of how you can calculate the overall heat loss, and again you need to take into consideration the fuel conversion efficiency, which I have a table of later, to then determine the overall heating capacity of your heating system. So here's that table where on the left hand side you see different fuels, including electricity, that you could use for heating greenhouses. It tells you what the typical unit is that we use. It tells you the price, and remember this is based on data that was collected in September of 2013, so the current prices may be different. It also tells you what the heat release is when we use a particular unit of this fuel source. So for example, for a therm of natural gas, we know that we get about 100,000 BTUs per therm from the heating system. But it also tells you the efficiency. The one but the last column shows you the conversion efficiency. So again, when you calculate your overall heating capacity, you need to take into consideration how efficiently we can convert the fuel source into heat energy before you can determine what the final boiler capacity or heater capacity needs to be. The reason I particularly like this table is because it compares the different costs of each of these fuel sources per common unit of energy that is being released. In this case, it's the million BTUs of energy unit. And so the very last column shows you the price of each of these different fuel sources, considering the conversion efficiency per standard unit of a million BTUs. And you can see here that natural gas and perhaps surprisingly coal are by far the cheapest fuel sources we can use at the moment for heating greenhouses. And wood, as you can see, is not very far behind. But for example, heating greenhouses on propane or number 2 fuel oil is significantly more expensive than natural gas or coal. Some growers have asked me how to calculate which fuel source is cheaper. And so I have an equation in this slide showing you how to calculate that. And perhaps it's easiest if we just go straight to the example. I compare the difference between coal, hard coal in this case, and natural gas. So you need to figure out what the price for coal for natural gas is first, which I found was about 50 cents per therm at the moment. You multiply that by the ratio of the conversion efficiencies, so it's 0.65 for coal and 0.80 for natural gas. And then you need to multiply it by the ratio of the heat value of those units, for those different fuel sources. So it's 26 million BTUs per ton of coal divided by 100,000 BTU per therm of natural gas. And if you do the calculation, you notice that the coal price should be less than $105.63 per ton in order to make a switch from natural gas to coal attractive. But keep in mind that this calculation does not take into consideration the delivery cost and perhaps a rebuild of your heating system necessary to switch from one fuel source to another. So this basically only looks at the cost of the fuel itself. There's a good piece of software called Virtual Grower that you can download for free, and I have on this slide the URL or the website address where you can find this piece of software that can be very useful for calculating the overall heat loss from greenhouse structures. So you can enter the dimensions, for example, the materials that your greenhouse is made of, the heating system, the fuel source, And you can also start planning your production, so you can lay out your production schedule, what crops you're going to grow, when you start growing them, and things like that for your particular location. And then the software is able to calculate your heating costs, and it can start comparing heating costs depending on different fuel sources or different heating systems or different greenhouse construction materials. So I think it's a very useful tool that you can start experimenting with to try to figure out what is happening in your greenhouse system and how you might be able to make changes to your greenhouse system to reduce the overall heating cost of your operation. We'd like to acknowledge the funding that was received for this effort by the USDA NIFA program.